When a Linux permission problem shows up, it often arrives with a very specific kind of frustration. It used to work, and now it does not. That phrase is valuable because it tells you the failure is likely tied to a change, but it also tempts beginners into guessing at what changed without evidence. Permission failures can be caused by ordinary mode bits, but the trickier ones often involve access control list, ACL, rules, file attributes, or account and group membership changes that are not obvious at a glance. That is why a simple check of owner and permissions might look fine while the operation still fails. In this episode, we will build a disciplined way of thinking about permission failures that helps you stop chasing the wrong layer. We'll focus on why ACL behavior can override or refine traditional permissions, how file attributes can block actions even for powerful accounts, and how account access changes can quietly remove capabilities that users assumed were permanent. The goal is not to memorize commands, but to internalize a set of questions that reliably explain why something used to work and how to restore functions safely. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A strong starting point is to remember that access decisions in Linux are often the result of multiple gates, not just one. Traditional permissions are based on ownership and mode bits that represent read, write, and execute for the owning user, the owning group, and everyone else. Many beginners learn these early and assume they are the entire story. In reality, additional mechanisms can refine or restrict those permissions, and those mechanisms can persist across file moves, backups, and policy updates. Access control list rules can add more detailed per user and per group permissions, and file attributes can impose restrictions that are independent of mode bits. Account access can also be constrained by group membership, account status, or policy restrictions that determine whether a user can even assume the identity needed to access a resource. When a failure occurs, your job is to identify which gate is denying access. This is why the phrase "why it used to work" matters. A change might have affected one gate, while leaving the others untouched, making the situation confusing unless you look beyond mode bits. Traditional permissions are still the baseline, so it is important to keep a clear mental model of how they are evaluated. Linux checks whether the user attempting the action matches the file's owner, and if so, it uses the owner bits. If not, it checks whether the user is in the file's group, and if so, it uses the group bits. If neither applies, it uses the other bits. This logic is simple, but it leads to subtle errors when group membership changes or when files are created with unexpected ownership. For example, a user might have been in a group that granted write access, but later that group membership was removed, so the file still looks permissive but not for that user anymore. Another subtle issue is that directories require execute permission to traverse, which means a user might have read permission on a file but still be unable to access it because they cannot traverse the directory path. Beginners often focus only on the file, but path permissions are part of the access decision. When you internalize these basics, you can quickly rule out or confirm the simplest causes before you move to more advanced ones. Access control list rules come into play when you need more precision than the traditional owner, group, and other model provides. An ACL can grant or deny access for specific users or specific groups beyond the primary owner and group, and it can also define default permissions for new files created in a directory. This is both powerful and dangerous for beginners, because it can create situations where two files in the same directory behave differently even though their mode bits look similar. A common misunderstanding is assuming that if the mode bits grant access, access must be allowed, but an ACL can create additional rules that change the effective permissions. Another misunderstanding is assuming ACL is only for special enterprise systems, when in reality it is often used quietly in shared directories to allow multiple teams to collaborate without changing ownership constantly. The result is that permission failures can appear after a file move, restore, or creation event that cause the file to inherit different ACL rules than before. If it used to work and now it does not, it may be because the effective ACL set changed, not because the owner bits changed. The idea of default ACL rules is especially important for explaining why new files behave differently than old ones. A directory can have default ACL entries that specify what permissions new files and subdirectories should receive, in addition to or in interaction with the traditional creation permissions and a mask behavior. If those defaults change, newly created files may lack the access that older files had, even in the same path. Beginners sometimes see this and assume the application is inconsistent, but the real cause is that the access rules applied at creation time were different. This is also why restores from backups can introduce surprise permission behavior, because the restore process might preserve ACL entries or might apply different defaults depending on how it is performed. The key reasoning skill is to consider the life history of the file. Was it created recently, moved recently, or restored recently? That history often determines whether default ACL entries were involved. When you treat permissions as something that evolves with file history, you can explain why it used to work without resorting to vague blame. File attributes add another layer that can block operations even when permissions appear to allow them. Attributes are special flags at the file system level that change how files behave, and they can impose restrictions that feel surprising. For example, an attribute can make a file immutable, meaning it cannot be modified or deleted, even by a powerful user, unless the attribute is changed. Another attribute can enforce append-only behavior, meaning data can be added but not removed or modified in place. These flags are often used to protect important configuration files or logs from accidental changes, and they can be a useful safety feature in hardened environments. The beginner trap is that attributes are not obvious from a simple permission view. So someone might see write permission and still be denied, then conclude the system is broken. In reality, the system is enforcing a stronger invariant. You may have permission, but the file's attribute policy forbids that kind of change. If a file used to be editable and now is not, an attribute might have been set as part of a security hardening step or an administrative action. That is why attributes belong in your mental checklist for mysterious permission denials. Account access problems are a third major category, and they are often the hidden reason behind the phrase "it used to work." A user might lose access because their account was locked, their password expired, their shell access changed, or their group membership was updated. In Linux, group membership is often the source of resource access because groups are used to grant shared permissions. If a user was removed from a group, or if a service account's group memberships were altered, access failures can appear even though the files never changed. Another subtlety is that group membership changes may not take effect for a user's current session until they start a new session, which can make the issue look inconsistent across terminals and processes. Beginners can become confused because one window works and another does not, and the difference is session identity, not file state. This is why account access belongs alongside file permissions in troubleshooting. A file can be configured correctly, but the user identity making the request might not be what you think it is, especially if privilege escalation or service accounts are involved. Privilege escalation also interacts with permission failures in ways that can surprise beginners. When you use a different identity to perform an action, such as running a command as an administrative user, you are not only changing user ID, but potentially changing group context and environment. This can cause an action to fail as a normal user and succeed as an elevated user, which is expected, but it can also cause confusion if the elevated context lacks certain group memberships that the user had. Beginners sometimes assume elevated means all access, but access can still be constrained by group memberships, policy, and additional security layers like SELINUX, which you studied in the previous episode. This is why permission troubleshooting benefits from being explicit about which identity is attempting the action. If it used to work when run under one account and now fails under another, the cause may not be the file at all. It may be a change in which account is used. In operations, these changes happen when services are reconfigured to run under different service accounts for security reasons, which is good practice, but it must be accompanied by correct access assignments. The phrase "why it used to work" also invites a change-driven timeline approach, because permission failures are rarely spontaneous. Something changed, a file was moved, a directory was recreated, an ACL default was adjusted, a hardening script set attributes, or an account was modified. The goal is to determine which class of change is most plausible based on the symptom shape. If multiple files in one directory suddenly became unwritable, it might be a directory-level ACL or attribute change. If only newly created files have the problem, it might be default ACL or a mass behavior. If one user is affected but others are not, it might be account or group membership changes. If a service fails but manual access works, it might be the service account identity lacking access. This is scope reasoning again, but applied to permissions. Broad versus narrow patterns help you locate the failure domain. Beginners often focus on the first file that fails, but the more productive path is to compare what works and what does not, because differences reveal the gate that is denying access. It is also important to avoid the beginner habit of fixing permission failures by opening everything up. When under pressure, people sometimes set overly permissive modes or change ownership broadly, which can restore function but introduce security risk and future confusion. This is especially risky in shared directories and service data paths, where loose permissions can allow unintended modification or data exposure. A better mindset is to aim for the smallest change that restores the intended access. If the issue is an ACL mismatch, the fix is to align the ACL to the intended users and groups rather than making the file world writable. If the issue is an attribute like immutable, the fix is to remove that attribute only if you understand why it was set and whether it was providing an important protection. If the issue is account access, the fix is to restore the correct group membership or account policy rather than changing file ownership to match a temporary workaround. This approach keeps your system defensible and maintainable. It also aligns with Linux Plus expectations because it demonstrates least privilege reasoning instead of shortcut reasoning. A practical way to keep yourself disciplined is to treat permissions as an intention you are implementing, not as a number you are manipulating. The intention might be that a service account can write to its data directory, but other users cannot, or that a team group can edit shared scripts while others can only read. Once you state the intention clearly, you can evaluate whether mode bits, ACL rules, and attributes support that intention. This makes troubleshooting less reactive because you are not just trying to make the error go away, you are trying to restore an access model. It also helps you avoid inconsistent fixes. For example, if you change ownership to make one user succeed, you may break another service that relied on group access. If you loosen permissions globally, you might solve today's problem but create tomorrow's incident. When you approach permissions as a design, you keep the system coherent. That coherence is what reduces future surprises when files are moved, restored, or recreated. As we conclude, the key outcome is that you can explain permission failures in a layered, evidence-driven way instead of treating them as mysteries. Traditional permissions determine access based on owner, group, and other bits, but they are not always the whole story because directories require traversal rights and group membership can change. Access Control List, ACL, rules can grant more precise permissions and can apply defaults that affect new files, which is why two files can behave differently even when mode bits look similar. File attributes can enforce restrictions like immutability or append-only behavior, blocking writes and deletes even when permissions appear to allow them. Account access changes, including group membership updates and service account identity shifts, can remove capabilities without changing any files at all, which is a common reason something used to work and now does not. The calm way to troubleshoot is to identify which gate is denying access, compare what works to what fails to reveal the pattern, and apply the smallest correction that restores the intended access model without weakening security. When you can do that consistently, permission failures become solvable puzzles rather than recurring emergencies, and that skill is central to real Linux administration and to Linux Plus success.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.